Welcome back to the next video, everybody. Today we're going to continue on pushing through chapter 8, looking at group representations versus algebra representations, and then looking at effective Chebotarev density. So let's get into it. It'll be a quick one today. Let's let n be a natural number. We'll take a coefficient ring A. Watch the last video to learn all you need to know about coefficient rings. And a profinite group pi. Okay, so the set of continuous group homomorphisms rho from pi to GLN of A is actually in bijection with the set of continuous A algebra homomorphisms R from the completed group ring A bracket pi to Mn of A, where Mn of A is the set of all n by n matrices with entries in A. Okay, more specifically, what is this completed group ring of pi with coefficients in A? It's the inverse limit over pi 0 and pi of the actual group ring A bracket pi mod pi 0, where the limit runs over all open normal subgroups pi 0 of finite index in pi. So what's a group ring? Let's say R bracket G. It's a free module with generators, the elements of G and scalars in R. Okay. So this is a nice thing to be aware of. We'll need this later in the chapter. All right. Perfect. So how do you prove this? It's actually pretty easy. The correspondence R maps to rho comes from restriction, right? Because pi is just isomorphic to some subgroup of the group of units in the completed group ring A bracket pi. Okay, so that means R restricts to a continuous group homomorphism of groups of units, which we'll call R star, from A bracket pi cross to Mn of A cross, but Mn of A cross is just GLN of A. So restrict this down and you get your rho. Okay, how do you go the other way from rho to R? You just use the universal property of group rings and the universal property of inverse limits. I won't get into that. Look up both of those universal properties and you'll see exactly that you get a map going the other way. That's the inverse of this map. Okay. Well, okay, so then given R or rho, one of the two, we have an underlying residual representation to rho into R, associated to rho into R. Okay, so we have rho bar, which is a map from pi to GLN of K given by reducing entries of the matrix mod MA. We already know this from last video, for example. But then we also have a residual representation attached to R, which is R bar, which is a map from A bracket pi to Mn of K. And again, that's just given by reducing the entries of the matrices in question mod MA, the unique maximal ideal of A. Okay. So proposition 1, the residual representation rho bar from pi to GLN of K is absolutely irreducible if and only if R is surjective. So you can see Bourbaki Algebra Chapter 8, Section 13 for the case A is a field, but then you can just extend to the general case using Nakayama's lemma. Okay, what do we care? How are we going to use this? Well, we get out of this the very famous Schur's lemma that we will use multiple times throughout the chapter and that we've already used in previous chapters. It says let rho from G to GLN of A be a continuous representation with coefficient ring A. If rho bar is absolutely irreducible, then any matrix in MNA which commutes with all elements in the image of rho is actually a scalar matrix. So a scalar matrix being a diagonal matrix, or a scalar multiple of the identity, if you like. Okay, so the proof is just the previous proposition, along with the basic linear algebra fact, the center of Mn of A is just the scalar matrices. Okay, perfect. So now let's move on and introduce Chebotarev density in kind of an effective manner that relates very strongly to these group representations. Let's let rho from pi to GLN of A be a representation where pi is profinite and A is a coefficient ring with residue field K of characteristic P. We'll assume that rho bar is absolutely irreducible, or equivalently by the proposition above, that the corresponding R from A bracket pi to Mn of A is surjective. So proposition 2, let's let rho prime from pi to GLN of A be a representation with the same character as rho. Okay, that is such that the A trace of rho of G is the A trace of rho prime of G for all G in pi. Then rho is isomorphic to rho prime. Oh, this is cool, right? So this is just saying, like, if you have two of these representations given by coefficient rings and their traces match for all G in pi, then they're actually the same representation up to isomorphism. That's quite a strong thing. We've already used that actually in previous chapters. So I've given you 3 references here you can go check out. We have a paper of Carriel, we have Sayre's book, and we also have the Cornell Silverman Stevens book giving an outline on page 253. Also, I like Curtis Reiner just in general, representation theory of finite groups and associative algebras, for a lot of the background you might be missing. Okay, but it gets better than this actually. So corollary, let's let rho and rho prime from some GKS to GLN of A be continuous representations. And suppose that only one of them is residually absolutely irreducible. Suppose further that the A trace of rho of Frobenius at L is equal to the A trace of rho prime of the Frobenius at L, not even for all primes though, just for all primes running through a set of primes outside S. And remember, S is a finite set of primes. And not even all primes outside of S, just all primes outside of S in a set of Dirichlet density 1. Then rho and rho prime are still isomorphic. Okay, so this is what I like to call effective Chebotarev density for Galois representations. We've used this already in previous chapters, and we'll use it in future chapters as well. For example, the proof of Falting's theorem. Okay, so the proof is just this is the above proposition along with the actual Chebotarev density theorem, which says that Frobenius elements are dense in Galois groups. Okay, perfect. So next time we'll look at the descent of Schur type lemmas. So I'll see you then, and thanks for watching.